welcome to this problem walkthrough. Today, we'll tackle LeetCode problem number 1008, where we'll construct a binary search tree from a given preorder traversal. This is an important problem that tests your understanding of BST properties and recursion. Let's dive in and explore the solution together. This problem requires us to construct a binary search tree, or BST, from an array of integers representing its preorder traversal. In a BST, the left subtree of a node contains only nodes with values less than the node's value, while the right subtree contains only nodes with values greater than the node's value. Both the left and right subtrees must also satisfy the properties of a binary search tree. The preorder traversal, as given in the input, means we visit the nodes in the order of root, then left, followed by right. Our task is to take this preorder list as input and return the root node of the resulting binary search tree. Let's illustrate the problem with an example. Suppose the input preorder traversal is 8, 5, 1, 7, 10, 12. The resulting BST would look like this. The root node is 8, with 5 as its left child and 10 as its right child. Continuing with the left subtree of 5, 1 becomes its left child, and 7 becomes its right child. For the right subtree of 10, 12 becomes its right child. This tree structure satisfies the properties of a binary search tree, and it matches the preorder traversal given in the input. Here's how the BST is constructed step by step for the first example. We start with the first value, 8, which becomes the root of the tree. The next value, 5, is less than 8, so it becomes the left child of 8. Then, 1, which is less than both 8 and 5, becomes the left child of 5. Moving on, 7 is less than 8 but greater than 5, so it becomes the right child of 5. The next value, 10, is greater than 8, so it becomes the right child of 8. Finally, 12, which is greater than both 8 and 10, becomes the right child of 10. In a similar way, the BST can be constructed for other inputs, such as the second example with preorder equals 4, 2. In the second example, we begin with the root node 4, which is the first value in the input. The next value, 2, is less than 4, so it becomes the left child of 4. Since there are no other elements, the BST is complete. Now, for the third example where the input is just 1, we simply create a BST with a single node, 1, as the root. Since there are no additional values in the input, the tree has no left or right children. These examples demonstrate how we use the properties of a BST and the preorder traversal to determine the placement of each node in the tree. To solve this problem, we must also consider the constraints and edge cases. The length of the preorder list is between 1 and 100, and each value lies between 1 and 10 to the power of 8. Additionally, all values in preorder are unique, ensuring that there are no duplicate nodes in the BST. For edge cases, if the input contains only one element, the BST will be a single node. If the input is sorted in strictly increasing order, the BST will have only right children, forming a linear structure. Similarly, if the input is sorted in strictly decreasing order, the BST will have only left children, also forming a linear structure. These edge cases highlight the importance of understanding how the order of values in the input affects the structure of the BST. To solve the problem of constructing a binary search tree from a preorder traversal, we need to understand two key concepts. First, the preorder traversal visits nodes in the order of root, left subtree, and then right subtree. Second, the binary search tree property ensures that all values in the left subtree of a node are smaller than the node, and all values in the right subtree are larger. Now, one approach we can consider is the brute force method, where we build the tree by inserting nodes one by one. Starting with the first element as the root, we process each subsequent element, traversing the tree recursively to find the correct position for each new value. While this method is conceptually straightforward, it has significant drawbacks. The worst-case time complexity is O(n) superscript 2, as each insertion in an unbalanced tree can take O(n), and we repeat this process for all n elements. Additionally, the recursion stack uses O(n) space. Though simple to implement, this method is inefficient for larger inputs due to repeated traversals of the tree during insertion. A more efficient approach leverages the properties of preorder traversal and binary search trees. This involves using a divide-and-conquer strategy with bounds to construct the tree. The key insight here is that for any given node, all values in the left subtree must be smaller than the node, while all values in the right subtree must be larger. To implement this, we start with the first element as the root and use a helper function that enforces bounds to determine where each value belongs. By maintaining bounds, we can directly decide if a value should go into the left or right subtree as we process the preorder sequence. Additionally, we use an index pointer to track the current element, which avoids redundant searches. This method achieves a time complexity of O(n), as each node is processed just once. The space complexity is O(n) due to the recursion stack. This approach is both efficient and elegant, though it requires careful management of bounds and indices. Another method to solve this problem is the stack-based iterative approach, which eliminates the need for recursion. Here, we use a stack to simulate the recursive construction of the tree. Starting with the first element as the root, we push it onto the stack. As we iterate through the preorder array, we adjust the stack to maintain the correct parent-child relationships. The stack's top element helps determine whether the current value should be added as a left or right child. This approach has a time complexity of O(n), as each node is processed once, and a space complexity of O(n) due to the stack. While this method avoids recursion, making it suitable for environments with limited stack space, it can be less intuitive and harder to implement correctly compared to the recursive divide-and-conquer strategy. Ultimately, we chose the optimized divide-and-conquer approach as our strategy. By using bounds to eliminate unnecessary comparisons, we achieve O(n) time complexity, making it ideal for large inputs. The iterative stack-based method, while efficient, is less straightforward, and the brute force method is simply too inefficient for practical use. The key insight that shaped our chosen approach was understanding how preorder traversal aligns naturally with a divide-and-conquer strategy. By enforcing bounds, we can directly partition the array into left and right subtrees, eliminating redundant traversals and reducing the complexity from O(n) superscript 2 to O(n). This realization was the breakthrough moment in designing an efficient solution. When comparing the approaches, the brute force method is easy to grasp but unsuitable for large inputs due to its inefficiency. The stack-based iterative solution is efficient and avoids recursion, but its implementation can be less intuitive. Ultimately, the optimized divide-and-conquer approach strikes the best balance between simplicity and performance. With its O(n) time complexity and clear alignment with the problem's constraints, it provides the most elegant and efficient solution to constructing a binary search tree from preorder traversal. To solve the problem of constructing a binary search tree from a preorder traversal, we start by understanding some key properties of the traversal itself. Preorder traversal always begins with the root node, followed by all nodes in the left subtree, and then all nodes in the right subtree. This order allows us to leverage the binary search tree property, where all values in the left subtree are smaller than the root, and all values in the right subtree are larger. Using this property, we can divide the traversal into segments and recursively reconstruct the tree. The first step is to identify the root from the first element of the traversal. Then, we partition the remaining elements into two groups, those smaller than the root, which form the left subtree, and those larger than the root, which form the right subtree. By repeating this process recursively, we can build the entire tree step by step. An alternative to the recursive approach is an iterative solution that uses a stack. This method optimizes memory usage and avoids the overhead of recursive calls. Before diving into the iterative method, let's break down the recursive process into clear steps. First, our input is the preorder traversal array. We define a helper function that takes bounds for valid node values. This ensures that as we construct the tree, we maintain the binary search tree properties. The base case for the recursion checks if the current value is out of bounds or if we've exhausted the array, in which case we return none. For the recursive case, we create a root node from the current value, increment our index to process the next element, and then recursively build the left subtree with updated bounds for smaller values and the right subtree with bounds for larger values. Finally, the recursive function returns the root node after both subtrees are constructed. This approach ensures the tree is built correctly while respecting the constraints of a binary search tree. Now, let's look at the iterative algorithm. Like the recursive method, it starts with the preorder traversal array as input. Instead of relying on recursion, we use a stack to keep track of nodes that are being processed. First, we initialize the stack, pushing the root node created from the first element of the traversal. Then, as we iterate through the array, we create a new node for each value. If the current value is smaller than the value of the last node on the stack, we attach it as the left child. Otherwise, we pop nodes from the stack until we find a node with a value smaller than the current value. This node becomes the parent, and the new node is attached as its right child. After attaching the node, it is pushed onto the stack for future processing. By the end of the traversal, the stack will have helped us maintain the correct structure of the tree, and the root node will represent the fully constructed binary search tree. There are several key insights that make this algorithm efficient. First, the binary search tree property allows us to partition the tree efficiently without sorting or additional operations. Second, the preorder traversal's root-first structure naturally aligns with the way we build the tree, making it easier to reconstruct. The bounds we use during recursion or iteration ensure that each node is placed in the correct position relative to its parent. In the iterative approach, the stack serves as a temporary storage to simulate recursion and track nodes that are still being processed. Time complexity for the algorithm is O(n), as each node is processed exactly once. Space complexity depends on the approach. The recursive method uses O(n) space for the recursion stack, while the iterative method also uses O(n) space for the stack that holds nodes during construction. Both methods are efficient and well suited for this problem. Finally, let's consider some edge cases. If the input array is empty, there are no nodes to construct, so we return none. For a single node array, the result is a tree with just the root node. If all elements are in ascending order, the tree will be skewed to the right, resembling a linked list. Conversely, if all elements are in descending order, the tree will be skewed to the left. These edge cases illustrate how the traversal order and values impact the structure of the tree. Handling these scenarios correctly ensures that the algorithm is robust and performs as expected across a variety of inputs. This solution constructs a binary search tree, BST, from a preorder traversal array efficiently. Let's break it down step by step. 1. Tree node class. Each node in the tree is represented by the tree node class, which has three attributes: val for the node's value, and left and right pointers for the left and right subtrees. 2. Solution class and main method. The BST from preorder method is the main function, which accepts a preorder list as input. This list provides the preorder traversal of the BST. 3. Recursive helper function, build. The build function is a recursive helper to construct the BST using the preorder list. Base cases. If index exceeds the length of the preorder list, or the current value at index is greater than the bound, the function returns none. This ensures that the recursive construction respects BST properties. Recursive construction. The current root node is created using the value at index. The index is then incremented to process the next value in the preorder list. The left subtree is built recursively, with the current value as the upper bound, since all left children must be smaller than their parent. The right subtree is built recursively, with the original bound passed down, since all right children must fit within the parent's bound. 4. Initialization and starting the build. The index variable is initialized to 0, indicating the start of the preorder list. The build function is invoked with an initial bound of infinity, allowing all values to be valid initially. 5. Output. The build function returns the root of the constructed BST, which is then returned by BST from preorder. This approach ensures that the BST is constructed in O(n) time, where n is the number of nodes in the preorder list. The recursive calls process each value exactly once, and the use of bounds ensures that the function adheres to BST properties efficiently. This makes the solution both elegant and optimal. Here, we start with the definition for a binary tree node, which includes an integer value and references to its left and right child nodes. The constructor initializes the node with a given value and sets both child nodes to null. Next, we define the main method, BST from preorder, which takes an array representing the preorder traversal of the binary search tree. To help us construct the tree, we use an index array as a pointer to track the current position in the preorder array. The method then calls a helper function, build, which recursively constructs the tree. It also takes a parameter bound, which is used to enforce the binary search tree property, ensuring that all nodes in the left subtree are less than the root value and all nodes in the right subtree are greater than the root value. If the index exceeds the array length or the current value violates the bound, the function returns null, signaling that no more nodes can be added in this part of the tree. In the build method, the first step is to retrieve the current value from the preorder array using the index pointer and then increment the pointer to move to the next element. This value becomes the root of the current subtree. We create a new tree node instance for this root. After that, we recursively construct the left and right subtrees. For the left subtree, we call the build method with the current value as the new bound, ensuring that all nodes in the left subtree are smaller than this root value. For the right subtree, we use the original bound passed to this method, which ensures that all nodes are valid within the constraints of the parent node. Finally, we return the root node, which now connects to its left and right subtrees, completing the construction of this part of the tree. To construct the binary search tree from the given preorder traversal, we begin by initializing the index to 0 and setting up the build function with an initial bound of infinity. The first call to build checks the value at preorder index, which is 8. Since 8 is less than the bound, we create a tree node with value 8 as the root and increment the index to 1. Next, we recursively build the left subtree of 8, updating the bound to 8. In this second call, preorder index is 5, which satisfies the bound condition. We create a tree node with value 5 as the left child of 8 and increment the index to 2. Now, we recursively build the left subtree of 5, updating the bound to 5. At this point, the preorder index is 1, which is valid under the bound. We create a tree node with value 1 as the left child of 5 and increment the index to 3. Finally, we attempt to build the left subtree of 1, updating the bound to 1. When we try to build the left subtree of 1, the value at preorder index is 7, which exceeds the bound of 1. This means the left child of 1 is none. Next, we attempt to build the right subtree of 1 with the same bound of 5. Once again, the value 7 is greater than the bound, so the right child of 1 is also none. At this point, we return the constructed tree node with value 1 to the previous recursive call. Back at the tree node with value 5, we now focus on building its right subtree with a bound of 8. Here, the value at preorder index is 7, which satisfies the condition. We create a tree node with value 7 as the right child of 5 and increment the index to 4. Attempting to build the left and right subtrees of 7 returns none for both, as the next value in the preorder, 10, exceeds the bound. We then return the tree node with value 7, followed by returning the tree node with value 5 to the root node. Now, we move on to the right subtree of the root node with the initial bound of infinity. For the right subtree of the root node, the value at preorder index is 10, which is valid under the bound of infinity. We create a tree node with value 10 as the right child of 8 and increment the index to 5. We then attempt to build the left subtree of 10 with a bound of 10, but the next value in the preorder, 12, exceeds the bound, so the left child of 10 is none. Moving to the right subtree, the value at preorder index is 12, which satisfies the bound. We create a tree node with value 12 as the right child of 10 and increment the index to 6. Since we've reached the end of the preorder list, both the left and right subtrees of 12 return none. Finally, we return the tree node with value 12, followed by returning the tree node with value 10. At this point, the entire tree has been constructed, and we return the root node with value 8. The resulting BST is as shown, with 8 as the root, 5 and 10 as its children, and further nodes 1, 7, and 12 forming the subtrees. In the second example, we use the same approach to construct a BST from the preorder traversal 3, 2, 1, 5, 4, 6. First, we create the root node with value 3. For the left subtree, we create a tree node with value 2, and then recursively build its left child as a tree node with value 1. Since node 1 has no children, we return to node 2, which also has no right child. Returning to the root, we now build the right subtree with value 5. For its left child, we create a tree node with value 4, which has no children. For the right child of 5, we create a tree node with value 6, which also has no children. The final BST is shown, with 3 as the root, 2 and 5 as its children, and further nodes 1, 4, and 6 completing the tree structure. To analyze the time complexity of constructing a binary search tree from its preorder traversal, we begin by considering the iteration through the preorder list. Each element in the list is processed exactly once as we increment the index in visit nodes. This contributes O(n) to the time complexity, where n is the length of the preorder list. Next, the algorithm makes recursive calls to construct the left and right subtrees for each node. In the worst case, where the tree is completely unbalanced, there could be up to n recursive calls, one for each node. Each of these calls performs constant work, so the recursion overhead also sums up to O(n). Additionally, we perform bound checks to maintain the BST property, ensuring that values in the left subtree are less than the root, and values in the right subtree respect the current bound. These comparisons take O(1) per node and are performed n times, contributing another O(n). When we combine these steps, the overall time complexity of the algorithm is O(n). Now, let's consider the space complexity. The primary memory usage comes from two sources, the recursive call stack and the tree node objects. First, the depth of recursion depends on the height of the BST. For a balanced tree, the height is O log n, while for an unbalanced tree, it can reach O(n). This means the recursive call stack contributes O(h), where h is the height of the tree. Second, for each node in the preorder list, a tree node object is created, and each object requires O(1) space. With n nodes, this contributes O(n) to the space complexity. Thus, the total space complexity is dominated by the larger of these two factors. In the worst case, where the tree is completely unbalanced, the space complexity is O(n) for both the nodes and the stack. In the best case, for a balanced tree, the space complexity is O(n) for the nodes and O log n for the recursion, which still results in an overall O(n) space complexity. When we compare different approaches to constructing the BST, the naive approach involves inserting each element from the preorder list into an initially empty tree. Each insertion requires a search for the correct position, which takes O(h) time, where h is the height of the tree. For n elements, this results in a time complexity of O(n*h). In the worst case, where the tree is completely unbalanced, this becomes O(n²). The optimal approach, however, avoids these repeated searches by directly constructing the BST using preorder traversal and bounds. This ensures each node is processed only once, reducing the time complexity to O(n). For space usage, both approaches require O(n) space for the tree nodes. However, the recursive nature of the optimal solution adds additional space for the call stack. In the worst case, this is O(n), while in the best case, it's O log n. Finally, let's examine the best, average, and worst cases for this algorithm. In the best case, the BST is perfectly balanced, with a height of O log n. This results in a time complexity of O(n) for processing the nodes and a space complexity of O(n) for the nodes plus O log n for the stack. In the average case, for a randomly structured BST, the height is typically O log n. The time complexity remains O(n), and the space complexity is O(n) for the nodes and O log n for the stack. In the worst case, when the BST is completely unbalanced, such as when the preorder traversal represents a sorted array, the height of the tree becomes O(n). In this scenario, both the time complexity and the space complexity are O(n). When working on this problem, there are several common mistakes to watch out for. First, it's crucial to respect the binary search tree properties. This means ensuring that for every node, all values in the left subtree are less than the root, and all values in the right subtree are greater than the root. Failing to enforce these constraints can lead to an invalid tree structure. Another frequent misunderstanding is confusing the input as an inorder traversal instead of a preorder traversal. Remember, preorder specifies the root first, followed by the left and right subtrees, which is key to constructing the tree correctly. Additionally, inefficient recursive solutions can arise if you don't use bounds to limit the recursion space. This can result in unnecessary backtracking and higher time complexity. A more subtle inefficiency is rebuilding subarrays repeatedly for each recursive call. This wastes both time and memory. Instead, you can use an index pointer to track the current position in the preorder array. Finally, don't overlook edge cases. Scenarios like an empty input array, a single node tree, or highly unbalanced trees, such as one where every node is in a straight line, can easily cause runtime errors or incorrect outputs if not handled carefully. Testing these edge cases ensures your solution is robust. Now, let's consider how this problem fits into a typical interview setting. One key takeaway is the importance of recognizing traversal patterns. Preorder, inorder, and postorder traversals are recurring themes in tree-related problems, and understanding their significance is essential. In interviews, it's not just about solving the problem but doing so optimally. While brute force approaches may yield correct results, interviewers expect you to aim for O(n) time complexity, which can be achieved by using bounds to limit recursion and avoiding inefficient practices like subarray slicing. Another aspect to consider is space complexity. Recursive solutions come with inherent stack space usage, whereas iterative solutions, using an explicit stack, provide more control over space. It's worth discussing these trade-offs in an interview setting. Additionally, proactively addressing edge cases demonstrates thoroughness. For instance, mentioning scenarios like an empty array or sorted input shows that you anticipate potential issues. Finally, this problem connects to other common tree-related problems, such as constructing trees from different traversal orders or validating a binary search tree. Familiarizing yourself with these related problems can deepen your understanding and prepare you for variations in interviews. There are several approaches to solving this problem, each with its own trade-offs. The most efficient method is a recursive solution that uses bounds to limit valid values for each node. By passing these bounds into a helper function, you can ensure that each node is processed only once, achieving O(n) time complexity. Another effective strategy is an iterative approach using a stack. This simulates the recursive process but avoids the use of the function call stack, which can help prevent stack overflow in cases of deep recursion. An iterative solution also gives you more direct control over memory usage, though it can be more verbose to implement. A less efficient but intuitive method is brute force, where you construct the left and right subtrees by slicing the preorder array into two parts. While this approach is straightforward for understanding how the tree is built, it has a high time and space complexity of O(n squared, making it unsuitable for large inputs. Each approach has its trade-offs. Recursive with bounds is efficient but uses implicit stack space, iterative with a stack avoids recursion but can be more complex to write, and subarray slicing is clear but inefficient. Understanding these options and their limitations allows you to select the best strategy for the problem at hand. Great job! In this session, we learned how to construct a BST from a preorder traversal using efficient algorithms. Remember, understanding traversal orders and recursion is key to solving such problems. Thanks for watching, and don't forget to like and subscribe for more coding insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!